Space has become trendy again between Elon Musk, who promises Mars, and NASA, which wants to return to the moon. People sell us colonies on the moon, bases on Mars, and even interstellar voyages within the next few decades. We get excited, imagine, and want to immediately plant a flag on Proxima B. But there is a truth never told on TV, a truth that might keep us forever grounded. What I am about to say today is not to break your dreams. Rather, it is for us to take a cold, hard look at the numbers, the laws of physics, the biological and technological constraints. They stand before us, and the interstellar future often dreamed of. Let's forget for a moment those spaceships hurtling towards Proxima Centauri in the blink of an eye. Forget about colonies on lush exoplanets. Unfortunately, that is not for us, and perhaps never will be. Let's start from the beginning. Even before thinking about reaching another star, there is a first obstacle, an invisible but immensely powerful monster to overcome. The gravitational well of our planet, that force keeps us on the ground, drops apples, and also maintains the breathable atmosphere around us. Thank gravity. But escaping it is a whole different story. As astrophysicist Yael Nazé emphasized in her lectures, we live at the bottom of a well, an invisible well, but an extremely deep energy well created by Earth's mass to escape that attraction. That was already a colossal struggle. Think of the Saturn V rocket that took the Apollo missions to the moon. Monsters 100 meters tall, weighing 3,000 tons at launch, most of which was fuel. 1 million liters of fuel burned in minutes. To reach about 28,000 kilometers per hour, the famous orbital speed. And all just to go around a small corner of the universe. Our low orbit is the very near suburbs. To go a bit further, consider our neighbor the moon, 384,000 kilometers away. You need to reach escape velocity of about 40,000 kilometers per hour. That's a whole different energy level. The Apollo missions, a colossal technological and financial feat, billions of dollars at the time, years of research and development, and the journey lasted a few days. Now look at Mars, our other neighbor, the red planet. Average distance, about 225 million kilometers. But it varies greatly from 55 to 400 million kilometers depending on the relative positions of the planets. You can't go to Mars anytime you want. You have to wait for specific launch windows. About every 2 years, we optimize orbits and travel times, occasionally using gravity assist. The journey lasts 6 to 9 months. 6 to 9 months in a tin can, exposed to cosmic radiation and the effects of microgravity on the body. We are starting to touch on the most critical issues when it comes to space travel. Mars is the distant suburbs. Getting there is already an epic, but it's still only the threshold of our cosmos. The solar system is vast. The Voyager probes launched in the 1970s took decades to reach the edge of our system. To begin with, just beyond the sun's direct influence, this region is called the heliosphere, and these probes have only just begun their journey into interstellar space. We see that leaving our little blue rock is already a high-level sport. The moon is a little trip. Mars is a real expedition, but it's all just a playground, the solar system's sandbox. To truly talk about interstellar travel, we have to completely change the scale. The nearest star to the sun is Proxima Centauri, a small red dwarf, probably accompanied by at least one planet, Proxima b. It has caused much debate because it lies in the habitable zone of its parent star. The problem is, close in astronomy doesn't mean much on a human scale. Proxima Centauri is about 4.24 light-years away. A light-year is the distance light travels in 1 year. Light is the fastest thing in the universe, about 300,000 kilometers per second. So a light-year is approximately 9.46 trillion kilometers. Multiply by 4.24 and you get 40 trillion kilometers. To visualize, if the sun were an orange in Paris, then Proxima Centauri would be another orange in San Francisco. And between them is empty space, an almost absolute void, cold, scattered with a few hydrogen atoms and cosmic dust. How long does it take to get there? Well, brace yourself. With our current technology, even the fastest, the Parker Solar Probe approached the Sunday. It reached a record speed of over 600,000 kilometers per hour. It would take about 6,700 years to reach Proxima Centauri, And I'm talking about a small probe. This is not a manned spacecraft. If you take a more conventional probe like New Horizons, which flew past Pluto, it would take 78,000 years. You're starting to see the problem. The distances are simply inhuman. And faced with the abysses of space, our current propulsion methods are tiny. This is where we hit the fuel wall, the tyranny of the Tsiolkovsky rocket equation. This equation is fundamental to astronautics. It says that to accelerate, an exponential amount of fuel is needed. The faster you want to go, the more fuel you have to carry. But the more fuel you carry, the heavier the rocket. And the heavier it is, the more fuel you need to move it. It's a terrible, vicious cycle. With chemical engines, the same kind that took humans to the moon and probes to Mars, we quickly hit a limit. Most of a rocket's mass is fuel. To reach even a tiny fraction of the speed of light, you would need such an astronomically huge amount of fuel. It itself would become larger than the observable universe, and I'm hardly exaggerating. So, what alternatives are there? Nicholas Pranzos, in his talks, explores several avenues, but each runs into enormous obstacles. Nuclear thermal engines, where we heat hydrogen with a fission reactor. That's already better than chemical, but not enough to change the game for interstellar travel. Project Orion in the 60s. Imagine propelling a ship by detonating small atomic bombs behind it. Powerful, yes, but imagine radiation, radioactive fallout, not to mention international treaties banning the weaponization of space and nuclear explosions. Nuclear fusion is the holy grail. It's the reaction that makes the sun shine. In theory, a fusion engine, like those in the Daedalus or Icarus projects, could achieve much higher speeds, possibly 10 to 15% of the speed of light. The problem is, we still haven't controlled fusion reactions on Earth to produce energy efficiently. Imagine a compact and reliable spacecraft engine. That's still distant science fiction. And even then, you'd need to carry huge amounts of fuel, like deuterium and helium-3, which actually, you'd have to go mine on the Moon or Jupiter. Welcome to logistics. And ion or plasma engines. They are very efficient in terms of performance, using little fuel for high specific impulse. Very useful for adjusting a probe's trajectory over years, but their thrust is tiny, about the weight of a sheet of paper. To accelerate a massive ship to interstellar speeds would take decades or even centuries of acceleration. And solar sails or photon sails, the idea is beautiful. Using the pressure of photons emitted from the sun or from giant lasers on Earth or in orbit to push a giant, ultralight sail. This project was invented to send nanoprobes to Proxima Centauri in 20 years using this technology. But we're talking about probes weighing only a few grams. For a habitable ship, the sail would have to be hundreds of kilometers in diameter, extremely thin and strong. And the big problem is deceleration. How do you brake when you arrive, when your only engine is a beam of light from a point behind you? Another approach is the Bussard ramjet, collecting hydrogen from the interstellar medium to fuel a fusion engine. This idea is very appealing in theory, as it allows for infinite fuel. But the density of hydrogen in space is ridiculously low. You'd need a giant scoop with a diameter of thousands of kilometers. This creates huge drag and cancels out part of the thrust, not to mention the technical complexity of such a machine. And antimatter in all this. The ultimate fuel, matter-antimatter annihilation, converts 100% of mass into energy. According to the famous equation E equals mc squared, in theory, just a few dozen grams of antimatter would be enough to propel a ship to the nearest stars. The problem is, we can only produce tiny amounts of antimatter, a few atoms at a time, in giant particle accelerators at enormous cost, trillions of dollars per gram. Then you need to store and handle it without ever letting it come into contact with ordinary matter. Otherwise, it's an explosion, a technological challenge beyond current understanding. You see the picture. This is not just a matter of ingenuity or budget. We are facing a physical wall, fundamental limits imposed by the laws of the universe as we know them. And we haven't even talked about what happens when trying to travel for a very, very long time or very, very fast. Suppose, miraculously, we develop a propulsion engine that allows a trip to Proxima Centauri, even though it might take centuries, even millennia. What does that actually require? It requires turning our ship into a kind of interstellar Noah's Ark, a world ship. An idea that has captivated generations of science fiction writers, but upon closer examination presents an enormous problem. Imagine, you put a community of people on board, a few hundred, maybe a few thousand individuals. You place them in a closed, self-sustaining structure for a journey longer than the entire history of human civilization so far. Generations of people will be born, live, and die on this giant tin can, hurtling through endless darkness, with the only hope that their great-grandchildren might find a new star. Would you want to try? The challenges are daunting. First is life support. A perfect closed ecological system is needed, capable of recycling 100% of air, water, food, and waste over centuries. No external help. We've struggled to do this on a small scale on Earth, so imagine in an isolated ship in the void. Even a small failure, a slight imbalance, could be catastrophic. Next are social, psychological, and ethical challenges. How do you maintain a stable, motivated society without major conflict in a stressful, confined environment over many generations? How do you manage governance, transmit knowledge, and preserve the mission's purpose when those arriving have never known Earth? They may have no emotional connection to it at all. That's fertile ground for the darkest dystopias. And then there's our biology. Our bodies are simply not designed for space, especially over very long durations. Cosmic radiation, those extremely high-energy particles bombarding the universe, is an invisible but fearsome enemy. On Earth, we are protected by the atmosphere and magnetic field. But in space, even with shielding, it significantly increases the ship's weight. Astronauts receive much higher radiation doses, significantly increasing risks of cancer, cataracts, and central nervous system damage. Zero gravity, or microgravity, is a slow poison. Loss of bone and muscle mass, cardiovascular problems, and weakened immune system. They cause vision disorders, and we've seen these effects in flights of a few months on the International Space Station. Imagine decades, even centuries. Artificial gravity systems, like giant centrifuges, are needed, adding to technical complexity and energy requirements. And reproduction in space, we don't know much yet, but initial animal studies are not promising. The combined effect of microgravity and radiation on fertility, embryonic development, and infant health, that's a huge unknown. And it could be an insurmountable barrier. But wait, there's more. Suppose we solve all those problems, build the perfect interstellar ship capable of protecting us and its inhabitants for millennia. And there's still a wall, a fundamental wall written into the laws of physics, the light barrier. The speed of light in a vacuum is about 300,000 kilometers per second. According to Einstein's theory of relativity, this speed is an insurmountable limit for any object with mass. We cannot go faster. Even just approaching that speed is a challenge. In terms of energy and practicality, imagine we want to reach only 10% of the speed of light, that is 30,000 kilometers per second. That is already enormous, far beyond the capabilities of our current propulsion engines. The kinetic energy required to accelerate a ship, even with a modest mass, to that speed is gigantic. And an equivalent amount of energy is needed to decelerate upon arrival. And even at these modest speeds, everything is relative. Other problems arise. The interstellar medium is not completely empty. There are dust particles, small meteoroids, hydrogen atoms. At 10% the speed of light, a dust particle a few millimeters across would release energy equivalent to the explosion of several tons of TNT. Our spacecraft would become a sieve, or worse, be crushed. Extremely durable shields or active deflection systems are needed, for which we have no design ideas. Vision and navigation also become headaches due to relativistic effects, like aberration and Doppler effect. The starry sky ahead of you will be completely distorted. Colors change. The stars concentrate into a small, bright cone. How to navigate accurately in those conditions? And communication, if you are halfway to Proxima Centauri, 2 light years from Earth, a simple message would take 2 years to arrive, and the reply 2 years later. 4 years for a single send and receive of information. Any help, any real-time discussion with Earth is impossible. You are alone, completely isolated. So, do you understand what I told you at the beginning of the video? We face challenges not only of technology, but also touching the fundamental limits of what our biology can endure. and what the laws of physics allow us to do, and we haven't even mentioned the truly strange things that relativity has in store for us if we venture too close to that famous limit speed. So, we have seen that even when imagining generation ships and solutions for biological and classical propulsion problems, we hit the light barrier and the dangers of subliminal speed. But science fiction and even some theoretical physicists like to play with limits. What if we could cheat? What if we could bend the rules of what seems immutable? That is when we enter the realm of truly strange relativistic effects and, shall we say, exotic propulsion concepts. One of the most famous effects of special relativity is time dilation generally. The faster you move relative to a stationary observer, or slower, your time appears to pass more slowly than theirs. This is counterintuitive, challenging our everyday experience. But it is a proven reality, measured by experiments with atomic clocks on airplanes or satellites. For interstellar travel, that seems like an opportunity if you can accelerate continuously at 1 g, corresponding to Earth's gravity. You would reach near light speed quite quickly. And there, like magic, time dilation begins to affect you on the ship. The journey to our galaxy's center, 27,000 light-years away, would take only about 20 years of your subjective time. You could even cross the observable universe, that is to say, billions of light-years in a single human lifetime. Hard to believe, right? Except that while you, the traveler, only age a few decades, hundreds of thousands or even 1,000,000 years have passed on Earth. Billions of years may have passed on Earth. You leave when you are young, and when you return, nothing is the same as before. It might be a form of immortality, but at the cost of absolute loneliness, a complete disconnection from your starting point. It is a journey from which you cannot return to what you once knew. And don't forget the energy required to achieve a constant acceleration of 1 g for many years. To ultimately reach these relativistic velocities, we again run into the problem of propulsion and fuel, but on a crazier scale. Yes, if it's truly impossible to go faster than light, or to play with time without drastic consequences, perhaps we can find shortcuts. This is where the craziest concepts appear, concepts that light up the eyes of science fiction fans. Wormholes, or Einstein-Rosen bridges, are theoretical solutions to Einstein's equations of general relativity. They envisage a wormhole, a shortcut through space-time connecting two very distant points. You enter one end and instantly appear at the other end many light-years away. Except that, as Nicholas Pranzos reminds us, currently this is purely mathematical. For a wormhole to be traversable and stable, exotic matter with negative energy density is required. What is that? Well, we have never observed it and do not even know if it exists. Most theoretical models suggest that such wormholes, if they form naturally, for example from primordial quantum fluctuations, they would be extremely small, unstable, and would collapse instantly or be filled with deadly radiation. We have no idea how to create one, or how to keep it open, or even how to survive inside it. The Alcubierre drive, warp drive, was popularized by physicist Miguel Alcubierre in the 90s. This is another attempt to cheat the speed of light. The idea is not to move the ship through space faster than light, but to warp space-time around the ship. We would contract space in front and expand space behind. The ship itself would remain inside this sort of normal space-time bubble and surf on that deformation wave. To an outside observer, the ship would appear to move faster than light. Again, in theory, the equations work, but here too there is a problem. It requires an astronomical amount of energy, and especially matter with negative energy density, that famous exotic matter. The amount needed is enormous, on the order of the mass of Jupiter converted into negative energy, not to mention other theoretical issues, like the fact that the pilot inside the bubble cannot control it, or reaching the destination could release a destructive amount of energy. These are beautiful equations, fascinating intellectual exercises for physicists. But at present, it is more like magic than applied science. We are far from even thinking about testing these concepts. So, does that mean we have to give up all hope? That science will never find new laws, new tricks, to overcome these limits? Well, perhaps not, but we need to be realistic. And the reality today is that the stars are astonishingly far away. The means to get there are, at worst, extremely difficult, at best, essentially impossible with our current understanding of the universe. So, where does all this lead us? Should we give up, put our dreams of space conquest in the closet, and resign ourselves to being forever trapped on our small blue planet? That is a bit sad, and not quite what I meant. The verdict, or at least the provisional verdict based on what we know today, it is interstellar travel, as we imagine in science fiction, with humans crossing the galaxy. For a few years, even a few decades, it seemed like pure fantasy. The distances are too vast. The energy required is enormous. Travel time is too long, dangers too many, and the laws of physics, as we understand them, are particularly stubborn. What is problematic today may remain problematic for a very long time, and even forever. But pay attention. I am not saying that our descendants will never have a revolutionary discovery, that they will never find new physics, new tricks to overcome obstacles that seem insurmountable to us. The history of science is full of surprises, revolutions that turn the seemingly impossible into possible. In fact, we learned to fly without wings, and we learned to harness electricity. We have learned to walk on the moon. However, there is a fundamental difference between overcoming technological challenges, no matter how complex, and violating the fundamental laws of the universe. There is the speed of light as a limit, conservation of energy, and the constraints of thermodynamics. They are not suggestions, they are the rules of the game. It is about placing hope for interstellar exploration on a future scientific revolution that we cannot even imagine today. It is a bit like buying a lottery ticket, hoping to become a billionaire to pay off debts. That could happen, but it is not really a plan. And at this point, paradoxically, the near impossibility of leaving our cradle could completely change how we view our planet. If we realize how difficult, even impossible, it is to leave Earth, then Earth for us is not just a simple pit stop. It is like a resource to exploit before moving on to the next. It is like a starting planet before colonizing the galaxy. No, it becomes what it always was, but perhaps we had forgotten. An island, an infinitely precious island, an oasis of rich and complex life in a vast and harsh cosmic desert beyond imagination. Understanding how difficult it is to leave forces us to see our planet differently. It is no longer a prison, but our only home. Perhaps the greatest journey, the greatest challenge of humanity, is not to fly to distant stars. Perhaps it is succeeding in living together on this small blue rock lost in the immensity, and at its core, perhaps that is the true conquest. Thank you for watching this video.